February 1943. Guadalcanal, Solomon Islands. Marine Corporal James Mitchell crouches behind a fallen palm tree, Japanese machine gun fire shredding the jungle canopy. His platoon needs to suppress that position now. He reaches for the ammunition box containing rifle grenade cartridges. His fingers find the pull tab. He yanks. The thin paper tape tears clean off. The box remains sealed under its wax coating. He claws desperately at the wax with his fingernails. 30 seconds pass. 45. A full minute. His hands are bleeding. The machine gun keeps firing. 2 men in his squad are already hit. This wasn't an isolated incident. Across the Pacific, Tarawa, Saipan, Iwo Jima, the same nightmare repeated itself daily. In the European theater, from the deserts of North Africa to the beaches of Normandy, American soldiers faced an impossible choice: waste precious combat seconds fighting their own equipment, or go without the ammunition they desperately needed. The enemy they could see. The enemy killing them was invisible, sealed inside boxes their own country had shipped them. The problem was staggeringly simple. Every ammunition box containing rifle grenade cartridges followed the same production process: seal the flaps with thin paper tape, leave a small tab for quick opening, then dip the entire package in hot wax for waterproofing. In theory, soldiers would grip the tab, tear it away, and access their ammunition in seconds. In practice, that paper tab, subjected to weeks of ocean transport, tropical humidity, temperature cycling, and constant vibration, deteriorated long before it reached combat zones. The Green River Ordnance Plant in Illinois alone produced millions of these boxes annually. Multiply that across every ammunition facility in the United States, and you're looking at tens of millions of boxes, each one sealed with the same fragile paper tape, each one destined for the same failure mode. The scale of the problem was vast, but the human cost was impossible to calculate precisely. Every second a Marine spent scraping wax off a sealed box was a second the enemy maintained fire superiority. Rifle grenade cartridges existed for one purpose: offensive suppression. They were meant to give American forces the tactical advantage to silence enemy machine gun nests, to create openings for advancement. When the delivery system failed, that advantage evaporated. And the failures weren't limited to combat. Ammunition stored on humid Pacific beachheads showed varying percentages of waterproof seal degradation, according to Quartermaster Corps reports. Boxes that sat for weeks waiting for forward deployment absorbed moisture through compromised seals. When soldiers finally opened them, if they could open them, they sometimes found corroded cartridges inside. The wax coating that was supposed to protect the contents had trapped moisture against the paper tape, creating the perfect environment for rust. The tragic irony. The military knew. By March 1943, the Ordnance Department's own committee meetings documented the problem officially: cover gasket failures, inadequate waterproof closures, packaging damage during transport. Field reports accumulated in Washington offices, each one describing the same pattern of failure. But knowing a problem exists and solving it are separated by an enormous institutional gulf. Here's what made this catastrophe particularly maddening. The failure point cost approximately 2 cents. A 2-cent piece of paper tape was compromising million-dollar ammunition supplies. American industry could produce Liberty ships in 45 days, B-17 bombers in a matter of weeks, and tanks by the thousands. But a paper tab on an ammunition box. That remained an unsolved problem. Supply officers tried variations. Some plants experimented with thicker paper tape. It still absorbed moisture. Others attempted double layering. The wax penetrated both layers, making removal even harder. A few tested waterproof paper coatings, which made the tape impossible to tear by hand, defeating the entire purpose of the quick access tab. Every attempted solution failed because they all preserved the fundamental flaw: paper cannot withstand operational military logistics. It doesn't matter how thick you make it, how carefully you apply it, or how precisely you perforate it. Single-layer cellulose structure exposed to humidity, saltwater spray, and temperature cycling will fail. Period. By early 1943, the problem had reached crisis proportions. Soldiers were adapting, carrying knives specifically to open ammunition boxes, warning new replacements about the tab failures, sharing techniques for scraping wax quickly. But adaptation isn't solution. It's acceptance of preventable death. Something fundamental had to change. The question wasn't whether the paper tape system was failing. Field reports proved that conclusively. The question was why nobody with authority was fixing it. The answer would come from the most unexpected source imaginable: a 52-year-old factory worker in Illinois, a mother of 8 with no engineering credentials, no military rank, and no institutional power whatsoever. But she had something the engineers and officers didn't have. She had 2 sons in the Navy, and she packed ammunition boxes every single day. The problem seemed absurdly simple. Ammunition needed protection from moisture. The solution seemed equally obvious: seal it with tape and add waterproofing. For generations, military logistics had relied on this exact principle. Paper tape was traditional, proven technology used since World War I for packaging military supplies. The wax dipping process was standard operating procedure across every ordnance plant in America. On paper, literally, the design made perfect sense. But there was an invisible enemy at work, one that military planners in their climate-controlled Washington offices couldn't see: the physics of material degradation under operational stress. Let's talk about what paper actually is. At the molecular level, paper consists of cellulose fibers arranged in a single-layer structure. Those fibers possess tensile strength measured in single-digit pounds per inch, barely enough to hold the paper together under normal conditions. There's no reinforcement, no elasticity, no resilience against vibration or repeated stress. Paper is fundamentally a static material designed for static environments. Now put that paper on an ammunition box bound for the Pacific Theater. The box gets loaded onto a cargo ship in California. During the 3-week voyage, it experiences constant vibration from the ship's engines. Temperature swings from 50 degrees F in the hold to 90 degrees F on deck, and humidity levels that cycle from dry to saturated as the ship crosses climate zones. The paper fibers absorb water molecules from humid air and swell. But they don't swell uniformly. Internal stress points form at microscopic levels. The adhesive backing, formulated for dry warehouse conditions, begins losing its grip. Temperature cycling makes it worse. As the box heats up during the day, the paper expands. As it cools at night, it contracts. But cardboard contracts at a different rate than paper tape. Each cycle creates microscopic tears along the perforation line. By the time that box reaches a combat zone, the paper tab has endured thousands of stress cycles, each one invisible to inspection, each one weakening the structure. Then add the wax coating. Hot wax penetrates paper fibers, theoretically creating a moisture barrier. In reality, it makes the tab harder to grip and impossible to tear cleanly. The wax stiffens the paper while simultaneously making it slippery. When a soldier pulls the tab, the weakened paper doesn't tear along the intended perforation. It tears at the stress fracture points created by all that environmental degradation. Result: a fragment of paper in the soldier's hand and a sealed box that now requires tools to open. Here's the instinct trap that fooled everyone: waterproof and protected seem like the same thing. They're not. Waterproofing the contents of a box requires completely different material properties than making the box accessible under combat conditions. One demands impermeability. The other demands controlled tearability. The wax and paper system optimized for the first while destroying the second. Military logistics officers measured success by a simple test: did the ammunition stay dry in storage? If yes, the packaging worked. They never asked the second question: can soldiers access it instantly under fire? That distinction between storage protection and operational functionality was the invisible gap that killed men. Factory supervisors who heard complaints about torn tabs assumed the solution was better paper tape or more careful wax application. They couldn't see that the entire material paradigm was wrong. You can't fix single-layer cellulose structure with better manufacturing. The material itself, paper, is fundamentally unsuited to the environment it's being used in. The psychological barrier was just as invisible as the physics. This was 1943, the height of American industrial mobilization. 6 million women had entered the wartime workforce, most in manufacturing roles. The organizational hierarchy was crystal clear. Engineers designed systems, supervisors managed production, and workers executed tasks. When supervisors heard suggestions from the factory floor, especially from women workers, they heard complaints, not engineering insights. The assumption was ironclad. If there were a better solution, the credentialed experts who designed this system would have found it. The people who saw the problem every day, the packers who watched tabs tear during quality checks, who understood combat conditions because their sons were fighting there, had zero authority. Meanwhile, the people who had authority, supervisors, military inspectors, ordnance engineers, never handled the actual product under field conditions. They saw test results from controlled laboratory environments. A box stored for 2 weeks at 70 degrees F and 50% humidity showed perfect seal integrity. Based on that data, they concluded the system worked. What they didn't test was 3 weeks at variable temperature, 90% humidity, constant vibration, and saltwater spray exposure. Multiple solutions failed because they all attacked the wrong variable. Ordnance engineers tried different adhesive formulations. The paper still degraded. They experimented with wax temperature and viscosity. Penetration depth didn't matter if the paper was already compromised. They tested alternative cardboard grades. The problem wasn't the box, it was the seal. Every failed attempt reinforced the belief that the current system was good enough. After all, if the Army's best engineers couldn't significantly improve it, maybe this was just the cost of doing business in wartime. What nobody in authority recognized was that the solution required abandoning paper entirely. The answer wasn't better tape, it was different tape built on a completely different material principle. Not cellulose, but woven fabric. Not single layer, but reinforced construction. Not water-resistant coating, but waterproof plastic laminate. The knowledge existed. Fabric-backed adhesive tapes had been manufactured for decades in medical and industrial applications. Johnson & Johnson had been making surgical adhesive tape since the 1880s, pressure-sensitive adhesive applied to cloth backing, designed to remain secure on skin while being removable without tools. The materials, the manufacturing expertise, the proven adhesive formulations, everything needed to solve the ammunition box problem already existed in American industry. It just took someone who understood both the technical problem and the human stakes to connect the dots. Someone who didn't care about hierarchy or conventional wisdom or staying in her lane. Someone who had nothing to lose and 2 sons to save. But first, the system had to completely fail at solving this itself. Early 1943. Green River Ordnance Plant, Amboy, Illinois. The complaints had been accumulating for months. Field reports from Pacific combat zones documented ammunition box seal failures with increasing frequency. Quartermaster Corps logistics officers noted varying percentages of waterproof seal degradation on boxes dumped on beachheads and exposed to weather for some time. The March 1943 Ordnance Committee meeting in Washington, D.C. officially documented the problems: cover gasket failures, inadequate waterproof closures, volume inadequacy for ammunition storage, and damage during handling and transport. The military knew. The problem was catalogued, analyzed, filed in official reports. But knowing and solving are separated by institutional paralysis. The ordnance engineers approached the problem exactly as their training dictated: systematic analysis of the existing design. Test different adhesive formulations. Experiment with wax temperature. Evaluate alternative cardboard compositions. Each modification received rigorous laboratory testing, controlled temperature, measured humidity, standardized handling procedures. And in those controlled conditions, marginal improvements worked. A special adhesive formulation showed 8% better moisture resistance. A modified wax blend penetrated 12% less deeply into paper fibers. Each small optimization was documented, verified, and recommended for potential implementation. But laboratory conditions aren't combat conditions. A sealed box that survives a week in a climate-controlled testing facility might fail within days on a transport ship crossing the equatorial Pacific. The engineers optimized for the wrong environment because they never experienced the right one. Not one of them had crouched in a foxhole with artillery screaming overhead, desperately trying to open an ammunition box with a torn tab and bleeding fingers. Meanwhile, government or inspectors made their rounds through ordnance plants. They verified production quotas, checked adherence to specifications, ensured quality control compliance. When Vesta Stute, a factory worker on the packing line, demonstrated her fabric tape prototype, the inspector saw exactly what his training told him to see, an unauthorized deviation from official specifications. His job wasn't to evaluate innovations. It was to enforce existing standards. He nodded, said, "That's all right," and moved on. The system was functioning exactly as designed, resistant to innovation, optimized for standardization, allergic to bottom-up suggestions. Plant supervisors faced different pressures. They had production quotas that increased monthly as the war intensified. They managed chronic worker shortages despite the influx of women into manufacturing. They answered to military contract officers who tolerated zero flexibility on delivery schedules. When Vesta approached them with her fabric tape solution, they saw a proposal that would require requisitioning new supply contracts, modifying established procedures, explaining changes to military inspectors, and taking personal responsibility if anything went wrong. The easiest response: "Your idea is fine, but that's not our decision to make. Pass responsibility upward. Let someone else take the risk. Meet today's quota, ship today's boxes, avoid today's complications." This is how institutions fail. Not through dramatic incompetence, but through 1,000 small decisions to avoid risk. The engineer optimizes measurable variables in controlled environments. The inspector enforces specifications. The supervisor protects production schedules. Each person behaves rationally within their role. Collectively, they create a system incapable of solving the actual problem. The tragic irony, if any single person in that chain had possessed both authority and frontline knowledge, the solution would have been obvious. But authority and knowledge were distributed to different people, separated by rigid organizational hierarchy. Knowledge lived on the factory floor, in the hands of workers who had no power. Authority lived in offices occupied by people who had never felt paper tape tear under their fingers, who had never imagined their own sons bleeding out while fighting a sealed ammunition box. It would take someone willing to bypass the entire system, to leap over supervisors, inspectors, ordnance committees, and military bureaucracy, and appeal directly to the one person in America who could give an order nobody would question. It would take a mother who understood that every day of institutional paralysis meant more soldiers dying from a 2-cent piece of tape. Vesta Oral Stout didn't look like someone who would change American military logistics. She was 52 years old in 1943, a mother of 8 children, living in the small Illinois towns of Sterling and Prophetstown. She had no engineering degree, no military rank, no institutional authority of any kind. What she had was a job inspecting and packing rifle grenade cartridges at the Green River Ordnance Plant. And she had 2 sons in the United States Navy. Clarence, aged 20, was serving with the Atlantic Fleet. Lowell, aged 26, was a construction mechanic in the Pacific Theater, the most dangerous posting of the entire war, where American forces were fighting island by island toward Japan, where every beachhead landing meant ammunition boxes dumped in humid tropical conditions. Every single day, Vesta went to work and packed ammunition boxes that might be opened by her own sons under enemy fire. Her observation came from repetition. She didn't see one tab fail, she saw hundreds. Day after day, shift after shift, the same pattern, thin paper tape applied to box flaps, small tab left for opening access, entire package dipped in hot wax. She felt the texture of that paper under her fingers thousands of times. She understood intuitively what the engineers in their Washington offices couldn't grasp. This design would fail the moment it faced real combat conditions. The insight that changed everything came from understanding function, not just form. Everyone else saw the ammunition box as a storage container that needed waterproofing. Vesta saw it as a combat tool that needed instant accessibility. The question wasn't, how do we keep moisture out, but how do we let soldiers in fast? She started experimenting at home. Using waterproof fabric tape similar to the medical adhesive tape she'd seen in first aid kits, she created a prototype seal on a sample ammunition box. The fabric backing provided tensile strength through woven fiber reinforcement. The waterproof coating eliminated the need for wax dipping entirely. Most critically, the tape was hand-tearable, strong enough to maintain seal integrity during transport, but designed to rip cleanly when pulled with deliberate force. No tools required, no careful peeling, no scraping wax. Just grip the tab and tear. She tested it on her kitchen table. Pull the tab, tears cleanly. Get the tab wet, still tears cleanly. Let it sit for a week in humid conditions, tears cleanly. The solution worked because it aligned material properties with functional requirements: woven fabric for strength, plastic coating for moisture protection, engineered tear line for accessibility. Armed with her prototype, Vesta approached her supervisors at the Green River plant. She explained the problems soldiers faced, demonstrated her solution, showed them how it worked under various conditions. Their response was the bureaucratic classic, "That's all right, but it's not our decision to make." She showed it to government inspectors, who rotated through the facility on quality control visits. Same response, nods of acknowledgement, zero action. The system had evaluated her idea and found it irrelevant, not because it didn't work, but because she lacked authority. Most people would have stopped there, accepted institutional inertia as immovable, returned to their workstation and kept packing boxes the old way, hoping their sons would be lucky, hoping someone else would fix it. Vesta understood something that her supervisors didn't. Every day of inaction meant more soldiers fighting defective equipment. Every day meant Clarence or Lowell might face that 60-second death trap. She made a decision that violated every norm of 1940s social hierarchy. She would bypass everyone: supervisors, inspectors, ordnance committees, the entire military-industrial chain of command, and write directly to President Franklin D. Roosevelt. February 10, 1943. At her kitchen table, Vesta composed a letter. She included hand-drawn diagrams showing the current design and her proposed solution. But the genius of her letter wasn't technical, it was emotional. She wrote, "I have two sons out there somewhere, one in the Pacific Island, the other one with the Atlantic Fleet. You have sons in the service also. We can't let them down by giving them a box of cartridges that takes a minute or more to open, the enemy taking their lives, that could have been saved." She wasn't making an engineering argument. She was making a moral argument. We are both parents. We both have sons in danger. This is our responsibility. The letter reached Roosevelt. He read it personally, and in a decision that showcased both presidential authority and genuine concern for frontline soldiers, he forwarded it directly to the War Production Board. Suddenly, Vesta's idea wasn't coming from a powerless factory worker. It was coming from the President of the United States. The same ordnance officials who had dismissed her prototype now faced direct presidential inquiry. March 26, 1943, just 6 weeks after Vesta mailed her letter, the War Production Board sent official notification. The Ordnance Department has not only pressed this idea, but has now informed us that the change you have recommended has been approved with the comment that the idea is of exceptional merit. 6 weeks. From kitchen table to presidential approval. The War Production Board tasked Industrial Tape Corporation, operating as Revolite, a Johnson & Johnson subsidiary in Milltown, New Jersey, to manufacture the new tape. Johnson & Johnson was perfect for this. They'd been making pressure-sensitive adhesive tapes since the 1880s, with deep expertise in medical applications where tape needed to be strong, waterproof, and removable by hand. Their founding mission was saving lives. Vesta's innovation aligned perfectly. Spring 1943. Production began. Military green fabric tape started rolling off assembly lines, cotton duck cloth sandwiched between rubber-based adhesive and polyethylene waterproof coating. Specifications matched Vesta's prototype exactly. Summer 1943. The new tape reached ammunition plants nationwide. Packers immediately noticed the difference. No more hot wax stations, no more fragile paper tabs. Just strong, hand-tearable fabric seals. Late 1943. Combat units started receiving ammunition boxes with the new seals. Response was immediate and enthusiastic. Soldiers could open boxes in seconds instead of minutes. But they discovered something unexpected. The tape was useful for everything. Torn Jeep fenders, tape it. Cracked rifle stocks, tape it. Holes in boots, tape it. Damaged aircraft panels, tape it. They called it 100-mile-per-hour tape because it could hold together equipment at vehicle speeds. Before Vesta, millions of boxes with fragile paper tape documented failure rates across all theaters, 60-plus seconds wasted per box under combat conditions. After implementation, near-zero seal failures, instant accessibility, unlimited multi-purpose field applications saving equipment and lives. The solution succeeded because it came from someone who understood operational reality rather than theoretical specifications. Vesta didn't need an engineering degree. She needed 10,000 repetitions of watching the problem occur. That experiential knowledge proved more valuable than any theoretical expertise. Approval was just the beginning. Transforming one woman's kitchen table prototype into military-wide standard required systematic change at every level of American wartime production. The training revolution began immediately. Workers at ammunition plants across the country, hundreds of facilities, hundreds of thousands of employees, had spent months or years perfecting the paper tape and wax method. Now they had to learn completely new procedures. Eliminate the hot wax dipping stations. Retrain packers on fabric tape application, sufficient overlap, firm pressure to activate adhesive, clean tear at the tab line. The beauty of Vesta's design was its simplicity. The new method was actually faster and easier than the old one. No waiting for wax to heat, no careful dipping, no cooling time. Just seal and ship. Within months, tens of millions of ammunition boxes were converted from paper to fabric tape. The Green River Ordnance Plant alone processed millions annually. Multiply that across every facility, and the scale becomes staggering. The largest packaging change in wartime logistics history, implemented in record time because one factory worker convinced the president. Johnson & Johnson's engineers continuously refined the formula based on field feedback. The military green color provided camouflage for ammunition stockpiles. Adhesive formulation was optimized for extreme temperatures, functioning in Arctic cold and tropical heat. Time 0.5s. Fabric weave was engineered for precise tear characteristics, strong enough to resist accidental damage, weak enough to tear cleanly with deliberate force. But the most remarkable development was mission creep in the best possible way. Soldiers weren't just using the tape for ammunition boxes. They were using it for vehicle repairs, equipment maintenance, personal gear, infrastructure, even medical applications. emergency bandage reinforcement, splint stabilization, temporary shelter repairs. The tape became a universal field repair tool, earning multiple nicknames: 100-mile-per-hour tape, gun tape, hurricane tape. Supply officers started requisitioning it in massive quantities, not for ammunition sealing, but for general maintenance. The measurable success was dramatic. Before, 60-plus seconds to open boxes with torn tabs, significant seal failure rates, single-purpose application, constant soldier complaints. After 5 to 10 seconds with clean hand tear, near zero failures, unlimited applications, enthusiastic adoption across all units. Even enemy forces adapted. Japanese and German soldiers began salvaging American duct tape from abandoned equipment and battlefield debris, recognizing its superior utility to anything their own militaries provided. The modern legacy transformed wartime expedient into cultural ubiquity. After World War II ended in 1945, military production rights were sold to commercial manufacturers. The tape underwent crucial changes, color shifted from military green to metallic silver, and the name evolved from duct tape, referring to cotton duck fabric, to duct tape, after civilians began using it to seal heating and air conditioning ducts. Ironically, later engineering studies by Lawrence Berkeley National Laboratory proved duct tape was actually ineffective for sealing HVAC ducts under sustained thermal stress. The one application that gave it its modern name was the one thing it couldn't do reliably. Today, the numbers are staggering. 2 billion rolls sold annually in the United States alone. Over $100 million in annual consumer spending. Available in dozens of colors, patterns, and specialty formulations. Applications ranging from emergency home repairs to professional construction to arts and crafts. Modern descendants of Vesta's innovation include aerospace speed tape, aluminum-backed pressure-sensitive tape used for temporary aircraft repairs, capable of withstanding high-altitude pressure and temperature extremes. A single roll costs $700 to $1,000 compared to $3 to $5 for consumer duct tape. But it's directly descended from the same principle Vesta articulated: strong enough to protect, terrible enough to access. The Apollo 13 mission in 1970 famously used duct tape to construct an emergency air filter adapter, saving the crew's lives when their lunar module's carbon dioxide removal system failed. Engineers on the ground identified common materials available on the spacecraft, including duct tape, and devised a solution astronauts could build with their hands. Vesta's principle held 250,000 miles from Earth. Hand-accessible, strong enough to seal, simple enough to implement under extreme stress. Modern military forces still issue duct tape as standard field equipment. Special operations units carry it on every mission. Emergency disaster response teams pack it in every aid kit. The International Space Station maintains supplies of space-grade fabric tape for emergency repairs. The universal lesson Vesta's story teaches goes far beyond adhesive tape. Frontline workers see solutions that credentialed experts miss. The people closest to operational reality, factory workers, soldiers, nurses, technicians, often possess critical knowledge that organizational hierarchy prevents from reaching decision makers. Vesta had no engineering degree, but she had 10,000 repetitions of watching the problem occur. That experiential knowledge proved more valuable than any theoretical expertise. Simple solutions often solve complex problems better than sophisticated ones. Ordnance engineers pursued elaborate optimizations of the existing paradigm. Vesta asked, "What if we just use different material?" Sometimes breakthrough isn't incremental improvement, it's paradigm replacement. Institutional resistance protects mediocrity. Every system creates antibodies against change. Vesta's idea was dismissed not because it didn't work, but because it came from someone without authority. How many other innovations died in that gap between frontline knowledge and institutional power? Vesta Stout received the Chicago Tribune War Worker Award for her innovation. Speaking to journalist Philip Hampson, she offered advice to other parents considering war work. You will do less worrying about your boys, and at the same time, you will be helping them. She reframed factory labor as an act of maternal love, a way to protect her sons from thousands of miles away. Her sons both returned safely from naval service. Lowell went on to operate a bowling alley and pool hall in Prophetstown, Illinois, the same small town where his mother was born. Vesta lived to see the post-war explosion of duct tape into civilian life, watching her wartime innovation become a household staple. She died on May 9, 1966, at age 75, in Prophetstown. By then, duct tape had become so ubiquitous that most Americans had no idea a 52-year-old factory worker had invented it. No monuments bear her name. No military bases honor her contribution. Her legacy lives in something far more profound. Every roll of duct tape in every toolbox, every emergency repair kit, every household drawer. Every time someone tears off a piece to fix something broken, a torn tarp, a cracked pipe, a damaged box, they're using Vesta's innovation. Every time an engineer designs a hand-tearable seal, they're applying her principle. Every time an organization listens to a frontline worker's suggestion, they're learning the lesson she taught. Somewhere today, a soldier in a combat zone tears open an ammunition container with a quick pull. The seal breaks cleanly, instantly. The ammunition is dry, protected, immediately accessible. The soldier doesn't know Vesta Stout's name, but in that moment, that effortless 5-second action, her determination to save lives continues, 8 decades later, exactly as she intended. One woman, one letter, one simple idea. 80 years of lives saved.